Okay, boys and girls, we're live with the third installment of Philosophy of Mathematics. And Danny is in control. Aren't you? Are we gonna
Yeah, so let me when I said I was ready, I meant that I wasn't ready. But let me pull up the
Damn
the,
philosophers.
well, no, that's dualism. That's dualism.
Oh, that is dualism.
When I said I was ready, I meant I wasn't ready.
Yeah, that's dualism. Yeah, philosophy.
Okay, let me stream my my stream. I'm almost there, guys.
What do you mean by stream?
Streaming my iPad.
Pulled up.
Okay, here we go. Let's do it. Wait, hello? All right, I have to put this button. I'm pushing the button, guys. Okay, start broadcast. Here we go. Share screen. We're good. We should be good to go. Okay. And my dog is whining, so I'm gonna try to mute myself as often as possible. But
I wanted to make a joke. They're so fucking bad, but I can't. No,
you better not. Maybe. You can see your connection. Oh, that's a nice graphic you got.
Excuse me.
oh, nice. I was muted. Okay, so Frege's logicism. Now, Frege, of course, was a bigwig in analytic philosophy, which we discussed earlier. The first thing is that he defended a version of Platonism. He was a defender of Platonism, and you can go back to the other episodes to get an account of what that was. But one thing that he was that Kant was not was he understood math to be analytic. Kant thought it was synthetic. Okay, and his whole project was to show that it was analytic by grounding, or I should say reducing math to logic, because everyone accepted that A is, and that a thing is a thing, or a bachelor's unmarried man, that's analytically true. And we can say that it's true by some kind of necessity with respect to a rule or a rule of logic or a law of logic. He wanted to do the same thing to math and say, hey, look, it's just the same thing. Okay. So he was what we call a logicist. He forwarded logicism. Okay. I have a little bit of notes on the, so he was a mathematician, logician, and philosopher. Now, remember last episode, Kant thought that the sort of mathematical truths were sort of given to us through this faculty of intuition, whereas things that were analytically understood were conceptually understood. So the way that you would know that a bachelor is an unmarried man is that the bachelor would contain the concepts of unmarried and man. He didn't think that was the case for mathematics. He didn't think, like, for instance, 5 + 7 contained the concept of 12. But Frege wanted to argue something like this, right? And one of the things that he did is he kind of understood analyticity differently than Kant. So remember, Kant was all about this containment, idea of conceptual containment. Frege reads Kant a little bit differently in this respect, in terms of understanding analyticity with respect to contradiction and logic, okay? Which is not which kind of excludes this containment idea of analyticity. So now, logicism is not a popular view, according to Linebo, the author of the book. I've highlighted it in red. The idea is that there are domains or cases in which logic applies, and there's no existent mathematical objects or statements. So the point is that if math is somehow logic, then math would also apply in those cases. But today's kind of outlook on that is that it doesn't seem to be the case that math is present wherever logic is present, or some kind of logical truth is present. So I think that's what he's saying there in terms of what I've underlined. All right. Okay. So now I highlighted this. Let's see. Although concerned with mathematical objects, mathematical truths are extremely general in their applicability. So this is one thing that Frege pointed out, that math seemed to apply in all domains. Remember I said that he considered mathematical objects to exist in the abstract realm, the third realm, but we could make predications, mathematical predications of all three realms. Okay, so like there are three rocks. That's the physical realm, right? The psychological realm, right, where we can count the number of beliefs, right, or something like that one may have, or the number of desires that they have with respect to an object. And then, of course, the abstract is where those mathematical objects are themselves exist, where they themselves exist. So there seems to be a kind of universality to math, and similar to logic. So there's one sort of similarity that might get you thinking, okay, maybe there's something to this logicist project. Okay. So let's go into the next page, on page 22. So during this time, and if you look at the very tail end of 21, math was sort of built on axioms, and these sorts of things that were derivative axioms, these mathematical truths of derivative axioms, were known as theorems. That's how I read it. So
yes.
Okay. Now let's look what I highlight here. In light of the axiomatic method, the epistemology of math splits into one question and I hate how he worded it there. There are two questions, one question and another question, which are two. The first question is, how do we know the axioms? How can we claim that we're rational in holding them? Now, it's a bit of an oxymoron, right? Because typically, like, a definition of axiom is that it's some kind of assumption. But this was starting to be challenged in the 19th century, where let's try to understand our axioms such that we can affirm them in some kind of way, be justified in them, right? Kind of logically reduce them. That's to say, understand their analyticity, their meaning. Okay, so that's one of the questions. The other question is, of course, how we get to the theorem. So there's the question of how we know axioms, and there's the question of how are we entitled to, in terms of where do we go from there? In other words, like, we have our axioms, okay, we have a story about them, we have our theory of them. Well, how do we get to the theorems, right? And what's that look like? Okay. So he gives an example of intermediate value theorem. Now, I'm not a mathematician, but I think there are probably people here that can explain it better than me. Does anybody want to give a jab at it?
I think for the best way I could do it is to share my screen and give like a visual.
Okay.
Let me pull up my my Chrome canvas, because I don't know why, sometimes I have a hard time putting what I'm visualizing in my head into words. No, that's not what
it seems, when I read the words, I was kind of like, I bet a visual would be better.
What they're talking about is order and continuity. So basically,
it deals with continuity, if you have a continuous function that contains the interval a and b, there's,
no matter how small,
if there are points that are greater than or less than some, I don't know how to put it into words. I just don't know how to put it into words, but I can sure as hell draw it.
Yeah,
well, it has to do with the idea of kind of like density. There's infinite density at any point on a continuous function. So that no matter how small the value you move away from this value, there'll be a value for that function that matches that. So you'll be able to find a result for that function that matches the number, no matter how small, like C or C plus E. If you take a very, very tiny E.
So this is how Wikipedia defines it. Let f be a continuous function defined on a, b, and let s be a number with f of a is less than s, which is less than f of b. Then there exists some x between a and b such that f of x equals s, which makes sense. So let me get my screen share here.
Sorry, I'm kind of ignorant about these things. This reminds me of Zeno's paradox. Is there any relation or no?
I
don't
know.
It's similar.
Okay.
That's the thing where if you keep cutting it in half, you'll never get there.
You're right.
Yeah.
Oh yeah, that. Let me know when the screen is up.
I don't have power. Mr. Steve has all the power.
I have great powers.
Okay, so you've got some continuous function. Hold on, let me do that so it doesn't go off the screen, because it's going to be important. And then you have, if I could get back to my A and B, and then you have some number S. You have a point there, and a point there, and a point there, and a point there, where I want to make sure I get this right. Yes. Where the function f of x is equal to s at those points. But like here, it wouldn't. Or here, it wouldn't. So that's essentially what it's saying, is that there will exist points on this function that will be equal to some number s.
All right. So the philosophical the philosophical relevance here is that for a long time, this was just taken to be intuitively true or self-evident, okay, for a long time. And then he brings up, so if we go back to my screen, Mr. Powerful, Omnipotent Speed.
Oh.
If we, he brings out a mathematician, I've never heard of this mathematician.
Bolzano.
Yeah, Bolzano. As sort of one of the first to kind of say, hey, let's not just cash this out in terms of intuition, in terms of self-evidence. Let's logically analyze it. Let's break it down and have a kind of theory of it, right? An understanding of it that goes past our sort of like self-evident intuition, right?
Mm-hmm. Can I make a comment quick?
Of course.
Just because it seemed to me that part of what this part of the book was saying is that we were used to understanding certain mathematical axioms, I guess you could say, in terms of their geometric intuition. And I think it was Bolzano that said, well, how can we go beyond that geometric intuition and get these axioms where we don't have to appeal to those intuitions? I thought that was really cool, because in calculus, you might learn certain things like what a derivative is in terms of the geometry, but in higher level calculus classes, you're not going to be speaking in terms of the geometry. You're going to be speaking in terms of the pure mathematics.
Oh, and so before there was that higher level calculus, all you had was sort of those geometrical intuitions or understandings. Is that kind of like the idea?
Yeah.
Okay. And that opened up mathematics to just anything. Basically.
And that's where, like what's mentioned in here, that's where analysis, like real analysis and complex analysis came from, is let's move beyond the sort of geometric, because almost all math can in some sense be understood geometrically, but let's move beyond that and try to understand it purely within the framework that we're talking. And that's where, if you take a class in real analysis, you'll learn about differentiation, continuity, limits, integration, not sets, series, but you'll learn that strictly within the terms of that, purely within the terms of that mathematics.
Interesting. Okay, so this was a big historical turn then. That during okay, and so Frege was on a part of this project. Is what I have here. There's the term for it. The rigorization of analysis. That's what. And I have two names here, and the first name is not really well written. That my So I'm gonna get back to y'all on that. But Jay Stockwell apparently has a very good some good writings on history of mathematics. So anybody interested in that? The other one is like whatever that gibberish is. Just I'll put it in the description of my video. But the point is that if you're interested in the history of mathematics, Jay Stockwell, it might be someone to look into.
Can you put it in the chat somewhere, or the private chat, and I'll put it in the description?
Yeah. There we go. Private chat. It's in so let's continue. So this is just more of what Leo was saying. And I'm just saying that Frege is part of this project, right? He's not he's going beyond the geometrical intuitions. He also, this is really interesting, he invented the first ever formal language, his conceptual writing, or Begriffsschrift. So that's interesting as well. So Frege is pretty big. Does anybody want to summarize? Did anybody read this paragraph here?
Yes. Like, did we read it, or does somebody want to read it?
Yeah, does someone? Well, oh no. Does anybody want to explain what's going on here?
Frege's academic career, is that where it starts?
Yeah. Mm-hmm. So, like, the idea is until Frege, this reason was largely informed and conducted in natural languages. Okay, but apparently that wasn't sufficient. Is what what I was getting.
Okay, I think sometimes I have to reread things just to understand.
Mm-hmm.
It seems that he's arguing that this idea that our axioms are purely analytic doesn't make sense. Like, how do we know that without appealing to some sort of intuitive principle, which seems to undercut this idea that they're purely analytic?
Right. So I get the idea is that Frege thought that the natural language could potentially hide some of our intuitive reasoning. So the idea is that developing a formal language sort of filters that out.
Mm-hmm.
I think that's the idea of this paragraph. So I thought that might have been important. So if we continue, in short, Frege's aim of gap-free proofs, like we don't know, no intuition jumps, right, led him to formulate what is now known as a formal system, which is an artificial language with clearly formulated axioms and inference rules, all described with mathematical precision. So this kind of term, formal system, is going to definitely come up again. There's a view called formalism, which we'll eventually get to, which Frege is not, right? But he's a logicist. But yeah, so that there's that's the kind of phrase that's been introduced in the text. It was under or italicized. And before this, the last person that did anything like this was Aristotle. Like Kant and was all the logic was Aristotelian logic. So Frege comes in and gives something brand new and something far more precise than what Aristotle was giving. Right? So we had nothing, and from Aristotle, which is like way, I don't know, 500, 600 BC. Maybe someone correct me on that. Maybe a little after, and then suddenly in the 1800s, we get a very precise formal system with nothing in between. So it's kind of crazy.
I just wanted to show a picture of Begriffsschrift because it's pretty intense. Judging, negation, conditionals, universal quantification, existential. Of course, we have different symbols for that now, but this got pretty dense. But anyway.
Yeah, which brings us to first-order quantifiers and second-order quantifiers. So these are supposed to be different kinds of generalizations. Does anybody, Leah, do you want to explain this?
Well, first-order and second-order quantifiers?
Yeah. Mm-hmm.
Well, I understood it with what was written here, and it seemed to me that a first-order quantifier, it generalizes a predicate, and a second-order quantifier generalizes what that predicate occupies.
All right. Do you want to go over the example he gives?
Oh, here for all x, there exists x such that. Okay, I got to remember what his something with Socrates being mortal. Yeah, Socrates is mortal. Symbolizes M as MS. Socrates is mortal. First order logic allows us to infer that there is someone who is mortal. There exists x such that x is mortal. Second order logic allows us to infer that there is some concept under which Socrates falls. There exists some concept such that S applies, or the concept applies to S.
So first order logic kind of gives you a set of things, and you can talk about the things in the set. And second order logic talks about the sets and the relationships. So second order logic introduces relationships, and it's also predicate logic or quantifier logic would be another way to look at it. And I'm not sure how far. Oh, they don't get into it too far, but you can say that x is an M, so x is a person or a man, and so you can say, and then you end up with quantifiers like E with the backwards E, which you're really good at, Leo.
There exists
an X such that X is a male. So, and so Frege's second order was sort of a way of talking about relationships among different sets and relationships, I guess, within a set. So it's
and properties, relations and properties. Yeah. Right.
Mm-hmm. Yeah. You really can't say like, there's a really good example in the Wikipedia. If you look up second order logic, where they talk about how you can, let's see, where is it here? That you can say, basically, you could talk about X being a cube, but you can't talk about all X being a cube. There was no language for it. So they started talking in terms of one level up from looking at things as individuals in the set. So I'm not sure if that makes any sense. But you could say that, what the hell is it here? I could share the screen.
Yeah, share the screen.
Yeah, I think I got a copy of it. Share screen. And of course, we'll see second order logic. Wikipedia is always really cool for information. So you can quantify over individuals, but not over properties. So that's kind of the key, that you can now quantify over properties. Like, let's see, let's replace the name of the variable, but we cannot do the same with the predicate. So if you have some relationship on cubes or on those individual cubes, you can't talk about that with first order logic. You can't talk about the relationship itself. So we're going one up with second order logic. And that's about as monadic second order. It gets weird from there. So.
All right. But I think that's sufficient. The fact that Frege really revolutionized the way that we do logic and math, right? And so big impacts on mathematics and philosophy there by developing those systems. And so so after he presents this, so down here, or not down there, but I think over here, we talk about the formal language, the Begriffsschrift, right? I think that's how you say it.
Begriffsschrift.
Yep. And then we get the foundations of arithmetic. Okay. So this is a big one. This is where the Logicist project really begins. The first thing that, he wants to establish, like what I said earlier, that mathematical statements are analytic. And so he wants to overturn the Kantian view that they're synthetic a priori. Okay. But he needs to, as I highlighted in the red, to extend the definition of analyticity. And this was what we were talking about. No more of this containing the concept, right? Stuff. So I have this highlighted. If the proof relies only on general logical laws and definitions, then the proposition is analytic. That's the idea for Frege, right? Oh, the only way I get analyticity if it's a matter of logical laws. So that means that to complete my Logicist project, I just got to understand the axioms or the mathematical truths as as just being understood in terms of logical laws and definitions. Okay, and then I completed my aim. Now, if he's unable to do that, what happens is that it becomes not necessarily contingent truth, but the idea is that it becomes that there's some other facts outside of the mathematical statement that make that serve as the truth conditions for that statement, and he doesn't want that. Let me just to quickly review. He wants to say that 2 + 2, or the square root of 9 is 3, is more like saying, a shape with sides is a thing with sides is a shape, and less like saying, Superman is Clark Kent. Mm-hmm. Okay, where Superman is Clark Kent, that can only be established based on how the world is, right? It could have been that the creator of Superman and Clark Kent, the DC makers, rewrote the story in a different way, or that even there could have. I mean, even if they didn't, that we need more information to show that Superman is in fact Clark Kent. If you have two people that have concepts of them that are divorced, right? So like the square root of someone might understand what the square root of 9 is and not understand that's threeness, right? And he wants to say that that seems to mirror the synthetic claims, like you can understand who Superman is but not know who Clark Kent is, and vice versa. But no, he's going to say, I'm going to show you why it's rooted in logic and thus it's analytic and not synthetic. That's just a reiteration of what a kind of current theme for the last 3 episodes of this book. But yeah, that's how I read this. There I have it highlighted where this concept of containment, conceptual containment, and analyticity is kind of being thrown away. And he actually, there's a citation here from Kant that seems to suggest that maybe there might be a more inclusive definition of analyticity. And that citation is right here if anybody's interested. I didn't read it. But apparently there is some basis for Kant for Kant thinking like this. But anyways, that's how I see it. Okay, a more serious complaint to which we shall return is that Frege has not told us nearly enough about the nature and extent of his general logical laws. So we're going to look at that in the next kind of when we like further his project in the later sections of the book. Yeah, but does anybody have any? I mean, maybe this was too quick of a.
Pretty short, but I think before we launch into the next one, probably a good stopping point.
Okay. Let's see. So, unless we don't have anything to say, let's just set up the next reading then.
Yep.
Okay. So, I got. I think we can go
2.3. Or is there?
How long is the chapter? No, we can't do. They can't do other chapters. No way. We all want to do till.
Where the hell did 2.4 go?
We can stop it. We can stop at Frege's theorem.
That's what I was going to say. I was about to say stop at some forms of realism, but that's not long at all. So we might as well throw that in there.
Yeah, and then this is a good. This probably will be the kind of the meat of the chapter. So we want to make sure we do that well. We don't want that the tail end of a reading. Okay, so we'll just do that. So summary. Let's just summarize really fast. The idea is that Frege. Okay. Let's in summary. Let's differentiate the views from Frege and Kant. So Frege thought that math was analytic Kant thought it was synthetic. So the implication here is that math reduces down to it is about concepts, which is Kant is saying that it's about intuition. So it's objects for Kant, right? The idea is that if you go back to, so let's go back to this reading really fast that we did last week that I really liked how Lenabo puts it. Let me find it. It's right here somewhere. Blah blah. Oh yeah, right here. Okay, so here this is our reading from last time. Since the knowledge is synthetic, it is about objects. It is about objects. Okay, which implies that if it is synthetic knowledge about objects, then for Kant, mathematical statements are objects understood not in terms of concepts. Okay, they're not simply conceptual. Now, I don't know if Frege wants to say something like they're simply conceptual. The point is that let me go back over here. The point is that if it's about concept, that's going to be in the realm of objects are in the realm of the world. Concepts in the realm of logical truth. Oops. Logical truths or propositions, as the philosophers might say. Like a proposition in philosophy is something that could potentially be true or false. It's not like, arguably they're objects from some blatantness, but the idea is that we understand that there's entailments with respect to propositions, but they're not like entailments of, the computer in front of you. It doesn't make sense that the computer in front of you entails another thing, right? But the proposition, there is a computer in front of me and it has entailments. So if it has entailments, we're talking about logic. Does that make sense, guys?
Yep.
Okay, good. Because if it doesn't make sense to you, it definitely doesn't make sense to anyone that's listening.
What I want to believe recently is that all of mathematics falls out of the real world, basically, in terms of like numbers fall out of the fact that there are two things two material objects in time and space, right? And then you extend that to start looking at time and space itself. And you start looking at Cartesian coordinates and things like that. And there are, you can axiomatize that. But then there are even deeper relationships because of the metaphysical reality of the universe we live in. There are a whole lot of other relationships like topology and all of that. And that, you can extend to a wide world of mathematics. But then at some point, you should be able to violate that and come up with an even more abstract math. And there's things like category theory, which is basically the mathematics of mathematics. And it seems like we are restricted somewhat to a real world, yet I think there's a way to step beyond that and consider what it might be if the metaphysics of this universe were not true. And in that case, you're starting to look beyond the Big Bang. You're starting to look at what the universe could be contained in, sort of, what the wider reaching mathematics would be. And this all seems to be available to human beings, which is really fucking weird. I mean, we're just apes on a slime ball, and we're able to somehow find these relationships in the world. It's pretty cool.
I will say that Frege considers. So we'll look at his. I think he should talk about his number. That's what his number. But the idea of number in Frege is very similar to existence, in the sense that if you were to predicate number of something, that's like predicating existence of something.
Yeah.
So if there are 7 rocks, that's like say that 7-ness is like on the same plane of property, the same kind of property as existence. So I will say that. Okay.
To talk about 7 rocks means there would have to kind of be 7 rocks in existence.
Yeah, I think he wants to distinguish them. I'm not so sure how. I'll pull it up next time. But the point is that it's what he might call a meta. Oops, that's not a meta property.
Yep.
Yeah, the odd thing is that there could be 7 rocks and there could be 7 planets. And there's some 7-ness about both those things.
Right, yeah. It seemed like there is set, with existence, right? Like Leo was saying, there is an apple, there is an orange. They both have this existence, this property of existence. Now, arguably, it's not a property,
so to speak.
Right? Yeah, arguably it's not a property, but he at least recognizes that it's not like a normal property. It's some kind of like second order property or meta property, right? But we should talk about that more next time.
Yeah.
Yeah, we're getting ahead of ourselves, guys.
All right. Yeah, I'm just kind of.
I won't tell you about the weirdness of minimal metaphysical models. You can develop minimal metaphysical models in programming, and you start to find some amazing places that you could go besides Cartesian coordinate systems. But anyway, we'll get into that later.
You can go
all right
far beyond Cartesian coordinate systems.
I'm going to stop sharing my screen.
Riemannian manifolds, Riemannian manifolds, Lorentzian manifolds, Hilbert spaces, Banach spaces.
Now, y'all are going to make sure I did my reading, but then as we get into Frege's project, my background knowledge starts to really go down. Like I'm going to be worthless in a few sections.
That might be the case with all of us.
Okay.
Well, me and Speed, when it starts getting into a lot of the predicate calculus and stuff like that, me and Speed should be able to handle that.
I know a few people with mathematical backgrounds. Maybe I'll ask, but unless I feel like you can handle, are y'all good enough? I'm not good enough. So
if we had a really good mathematician, it would probably break the project or hurt the project rather than us trying to kick around and figure it out ourselves. So
break the project?
Yeah. If you had a really good mathematician or already understands it, he probably wouldn't be able to fucking explain it to us.
Well, we'll see. I know a few. I know someone.
Yeah, you could drag one in and we could see what he has to say.
Yeah. Okay.
Yeah. He can embarrass all of us. So somebody could really embarrass me on category theory. Damn, I had trouble with that. But so what do we want to do? We want to end her?
I would say yes, because I do need to talk with Peter.
Yeah, we can. This is fine.
Oh, is Peter here?
No.
Oh, okay. Anyway, okay. So you're going to talk to Peter about OBS, I'll bet.
I honestly don't know. He asked me. Your
shitty channel has 300 subs.
Mm-hmm. It's a really shitty channel. Don't subscribe.
Yeah, I know. Okay. Anyway, guys, so we're going to end the broadcast. Goodbye, boys and girls.
Bye-bye.
All right.
Hey, 12 people showed up this time. That's good. It's better than before.